In the name of God, we're going to continue today with the topic we're going to address in this part, the starting point, flux of gas molecules. Okay? For us to get to an expression for this based on the kinetic theory of gas, as I've explained earlier, we're going to split the task into subtasks called A, B, C, D up to F. The first part is like A, and it's just this probability density, the Maxwell-Boltzmann probability density, which we have derived earlier. This is going to be very useful. We're going to use it a lot of time. And yeah, so let's go to the next page to talk about molecular flux. We want to drive a formula for this. Sorry. And yeah, so the first point is, as I've mentioned, we have, let's say, step A. Step A, we need this probability distribution, f of v. So this is the probability of finding a test molecule to have speed between v and v plus dv, right? So that f of v times dv is the actual probability, right? And the next step, B, is that if we are given like a small letter n to represent the number density of molecules, so this is going to be capital N divided by V, and big N is like the total number of gases, V is the volume of container, right? So with this we can compute, we can have this expression like n times f of v dv to be like the average number density. Yeah, so this is average number density for the system of gas under consideration. Average number density of, say, to be complete, average number of density of molecules with speed inside the range v to v plus dv, right? Hopefully you can derive this. It's very easy. So it's like computing the average of sort of average of the number density, right? So AB, as simple as that. C is the next step. For C, the target is we would want to compute an expression to represent probability of molecules traveling at angles between theta and theta plus d theta. So remember, if we consider a container of gas, yeah, there are various gas molecules in the container, right? I can take some direction to be a reference direction. Okay, we're going to choose or set what that direction is later on. For now, we take it to be arbitrary. So we have a reference direction, right? So if this reference direction, if I consider it to be this, going vertical, right? One can consider various molecules. Let's say there is a molecule moving with some speed v, right? So this molecule, the velocity v, what is the angle the vector v suspends with the reference direction? So this is like theta. So we can consider like a range. Theta is going to be a continuous variable. As usual, for continuous variables, we usually consider range, not absolute values. So if this is a theta direction, yeah, let's call it theta direction. And then, so we consider gas molecules which are moving at an angle that lies in this region. So between theta and theta plus d theta, right? So this is d theta, right? We would want to compute the probability of getting molecules to be traveling within this range of angle d theta. In order to do this, there are some points we need to consider. That so in 3D, actually, it's going to be a solid angle. What I have written here is kind of one-dimensional. So such particles or such molecules will be traveling within some i.e. molecules traveling within some solid angle. So this is going to be a differential solid angle, d omega, and by definition, this is going to be dA all over r squared. Right. We can make a recap about this. So, for example, recall, I'm going to start with the concept of an angle itself. An angle in a cycle, theta, is usually defined as theta is equal to S all over R. So let's consider that there is a cycle somewhere. This is center of the cycle, and then there is an arc, which is what we're going to consider. This arc is part of a cycle. It kind of sustains an angle theta. So this is theta. The length of the arc is S. The radius of the cycle is R. So theta is defined this way. The unit of theta is in radians. And so one can consider, for example, the total angle sustained by a complete cycle. We know that this is going to be 2 pi, so 360 degrees, or 2 pi radians, right? And for a complete cycle, the arc is going to be the circumference. So maybe I can write theta for complete cycle is going to be circumference, it's the length of the arc, so 2 pi r divided by r. This is how we derive this to be 2 pi radians, right? So this is one thing to recall. And two, we can move to the solid angle case. A solid angle, for the case of a solid angle, instead of considering a cycle, which is one-dimensional, we're going to consider like a sphere. Okay, a cycle, the length, like talking about the line making the cycle, it's a one-dimensional space, right? But the cycle lies on a plane. For solid angles, we're going to talk about a sphere. So sphere is 3D, and the surface the surface which the solid angle was sustained will be sustained by a surface, right? And the definition is that solid angle omega is defined as the area divided by r squared. The unit is radians, right? So A is like the surface area covered by the solid angle, right? And r is like the radius of the sphere, and one can see that the total solid angle for a sphere is going to be the surface area of a sphere, which is 4 pi r squared divided by r squared. So the total is going to be 4 pi radian, right? And it's from here that we derive the omega is going to be dA divided by r squared. So for a fixed radius, this is easy to see. Okay, I go to next page here. Now, if I try to draw something like a sphere, let's assume this is a sphere somehow, and the reference direction I was mentioning earlier, if we consider it to be these dashed lines, the reference direction, right? And one can consider like a molecule. One can consider, okay, the theta, which is corresponding to the solid angle under consideration. So we have theta here, and let's say there is d theta. Okay. So this little one here is d theta. And on a sphere, this is actually going to make an annular path, an annular kind of cut. So if I try to draw this like a sphere, I think it's messy, but hopefully you can get what I'm talking about. the differential solid angle, the omega, which we define to be dA divided by r squared, is going to be equal to, so I need to compute the area. The area due to the omega is going to be area of this annular cut. Okay, so to compute the area of this annular cut, it's going to be like we have, how can I do that? Maybe to draw something again. Sorry. Let's the annular cut is going to be something like this. So it's the this shaded area, part of the sphere. In a sense, I will need this radius. So from the center, okay, this radius is going to be r sine theta. You can kind of imagine that over here, drawing. So we have an angle subtended by r to be theta, and I need to compute the radius of this annular cut. The radius of this annular cut is going to be r times sine theta. Okay, so the differential solid angle is going to be circumference of annular cut times r d theta. Okay. What is r d theta? So r d theta, where is it coming from? Actually, it is some sort of this. I hope you can see this length. What value is it going to be? You can get this actually from that little d theta if I blow it up. So blowing up d theta in here, it's going to somehow, on the surface of the sphere, it's going to subtend an arc somehow. Okay. And the length of this arc is going to be, if this is r, so this is going to be r d theta, right? And in order to compute the area of this annular cut, the area of the annular cut is going to be circumference of the annular cut times the width of the annular cut. So the width is here, okay, which is r d theta. And if we can compute that, we need to divide by r squared. Okay, and so the circumference is going to be equal to 2 pi times radius. So the radius is r sine theta, radius of the annular cut circumference, so 2 pi r sine theta times r d theta all over r squared. Okay, and the answer, it's going to be equal to 2 pi sine theta d theta. Okay. So this is the solid angle in terms of theta, okay, and d theta. So remember, we're considering molecules traveling at an angle between theta and theta plus d theta relative to some reference direction. We want to compute probability, so the next step is, I should explain this, if all molecules are equally likely to be traveling in any direction, so the system is completely isotropic. Okay, remember the container of gas molecules, we have gas inside this container. So the assumption is that these particles are moving randomly, completely randomly, and independent of each other, and they are moving in a way that the likelihood of each molecule to be traveling in any given direction is the same for all of them. Okay, so given this assumption, then the probability of a molecule to be traveling within this range of theta and theta plus d theta. Okay, this probability is going to be equal to the fraction of molecules whose trajectory kind of lie within the differential solid angle d theta, right? So we're going to define some solid angle as we've done here, d theta, right? And we compute the fraction, the theta, sorry, the omega fraction. This is the elemental differential solid angle divided by the solid angle, the total solid angle. So in 3D, kind of a spherical thing. So this is going to be the omega divided by 4 pi. Okay, and if we substitute the expression derived above, this is going to be 2 pi sine theta d theta divided by 4 pi, and so this is going to be equal to 1 over 2 sine theta d theta. Okay, 1 over 2 sine theta d theta is going to be the probability of a molecule to be found traveling within theta and theta plus d theta. Okay, so this is C. Remember, A, point number A is like the probability of finding a molecule to be moving with speed values between v and v plus dv. Okay, and this is Fv times dv. Fv is the Maxwell-Boltzmann distribution. Okay. And B is the average number density, right? If you have number density for the gas, and N times f of v dv is going to be the average number density. And now we have C, which is the probability of finding a molecule to be traveling within an interval, angle interval, theta and theta plus d theta, right? So this is 1/2 sine theta d theta. Okay? So the next thing we're going to compute is point D. Point D is about average number density of molecules with velocity between v and v plus v, and also traveling at angles between theta and d theta, and between theta and theta plus d theta. So for D, we're going to combine two things, right? We're going to combine like B and C, right? What is B? B is average number density of molecules with velocity between v and v plus dv. Okay, so on top of that, we want molecules to, so let me go back here. We need molecules such that their velocity, let's say v star, is in the range v and v plus dv. Okay, and so this and is very important. We're going to use the probability rule, and we want molecules that are traveling relative to some specific direction, right? And the angle which they subtend with respect to that direction, if we call it theta star, the values of this theta star should be between theta and theta plus d theta, right? So the key point is this and, which is very easy. We're going to take the result, since we're dealing with probabilities, sort of average number. Let me write it here. The average number density of molecules with speed between v and v plus dv, and traveling at angles between theta and theta plus d theta. This quantity is going to be equal to n f of v dv times 1/2 sine theta d theta. Okay, so this is about point D. The next step, point number E. Remember, the chosen reference direction was arbitrary. Now we're going to fix it. Okay, we're going to fix it. So we let our reference direction to be perpendicular to a wall. So we consider a wall, let's say one of the sides of the container of the gas, and assume that the wall has an area A. Okay. And for point E, the task is we would want to kind of compute number of molecules traveling with speed between V and plus dV, and traveling at angles between theta and theta plus d theta with respect to the direction, and that direction is a direction perpendicular to a wall of area A. Yeah. So I can sketch somehow. Let's consider, let's say there is something moving here, okay. And supposing this is the wall under consideration, right. So if this is the wall, and the area, we consider this from here to here. Let's say the length is kind of a square root of a. Since the area of the wall is a, we can consider approximately the wall to be a square root of a. Right. And so we choose a perpendicular direction. So this is our direction, which is perpendicular to the wall. And supposing this is V for some molecule traveling at an angle theta. So we have theta here. Okay. And our reference direction, remember, is going to be, let's say, going that way. Reference direction, right? Okay. So actually, for a molecule with speed v, after some time interval dt, it is going to travel a distance of v times dt. Okay, so this length, we can consider it to be v times dt. Okay, and with this sketch, we want molecules, remember, traveling with speed between v and v plus dv, and also traveling at angles relative to some reference direction. The values of the angles have to lie between theta and theta plus d theta. Okay. And now we want to consider out of such molecules, we want the ones which are kind of hitting a wall. So for point D, what we want is that we need to kind of sieve out molecules such that they have V in V to V plus dV, right? And have theta star to be between theta and theta plus d theta, and also heating. So out of the so many molecules with these properties, V in this range and theta in that range, not all of them are going to hit the wall. So we want only the ones which are going to hit the walls. Hit the wall, hitting a reference area A. So this can call it hitting the wall, right? So these are the three things we want. In order to get that, the number of molecules with these three features, again, I'm repeating myself. This is feature number 1, this is feature number 2, this is feature number 3. 1, speed has to be in this range. 2, direction have to be in this range. And 3, we need molecules hitting a reference wall. Okay. Now, we should consider this point that within the time interval dt, such molecules will kind of sweep out a volume volume perpendicular to the wall, this is going to be something like area of wall times length traveled by molecules. So this is going to be something like the area is A and the length is going to be V cos theta d theta, right? So the length traveled is V d theta, right? But we take the length in the direction which is perpendicular to the wall under consideration. Okay. So with this formula, then the average number of particles with velocity between v and v plus dv and trajectory within theta and theta plus d theta, which hit a wall. So hitting a reference wall with area A within time dt is going to be equal to, so number of average number of molecules. The average number of molecules with properties 1, 2, 3, so to say, where 1 is this, 2 and 3. With these properties, that average number of molecules is going to be equal to A V cos theta d theta times n f of v dv times 1/2 sine theta d theta. Okay. So with this, we can conclude that the differential element for flux. If I let flux to be phi, so element of flux d phi, this is what we want to compute, right? D phi is going to be equal to this number of molecules divided by area divided by time. So within time interval dt, what is going to happen is that the phi is going to be equal to this expression divided by a dt. Sorry, this is d theta. No, dt d theta. Okay, and the elemental flux is then going to be equal to v cos theta n f of v dv times 1 over 2 sine theta d theta. So this is the element of flux, like number of molecules hitting specific area per time with velocities between like v and v plus dv, or speed instead of velocity, and with trajectories having theta within theta and theta plus d theta. So from here we can go on to compute the flux of molecules. It's just a matter of integration. So we integrate or sum out the different d thetas to get the result that we want. So that result is going to be element F, A, B, C, D, E, F. So we are now on F. Phi, big phi is equal to molecular flux, and which is number of molecules. Definition of flux is number of molecules divided by area under consideration times time interval. Okay, so based on the elemental flux we have derived a few seconds back, the total flux is then going to be something like this. We just integrate over speed from 0 to whatever values. So integrations from 0 to infinity, and sum over the different possible angles which the molecules sustain. And so the theta is going to be from 0 to pi over 2. We choose pi over 2, pi divided by 2, because we want molecules actually to be the ones hitting the wall, right? If you go beyond 90 degrees, those molecules with theta greater than 90 degrees will be traveling in the opposite direction to the reference direction we have chosen, right? So the theta integration is from 0 to pi divided by 2, and then the cos theta and f of b 1 over 2 sine theta, right? So this is going to be n divided by 2 integration 0 to infinity dv v f of v times this integration 0 to pi by 2 d theta cos theta sine theta, right? And hopefully you can easily see that this is the average, what we have done before. So F, remember, is the Maxwell-Boltzmann distribution. So this integration is like going to be the average speed of molecules. And this integration, you can check to do it. It's going to be equal to 1 divided by 2. It's equal to 1 over 2. So you can solve it by letting some, say, u to be equal to sine theta, and you compute du is going to be cos theta d theta, and then the integration is going to change into something like 0 to 1 u du, and that should be 1 over 2. So putting in these results, we can conclude that the flux, the molecular flux, is going to be 1 divided by 4 times n, the number density, times average speed of molecules, right? So this is F, A, B, C, D, E, F. F is done, is the molecular flux, right? And if we recall that for an ideal gas, we have derived earlier an expression for the average speed. It's going to be square root of 8 kBt divided by pi times m, mass of the molecules. Then, like, substituting this in, you can see that we can write phi to be something like n times kb t divided by 2 pi m. You can please check this expression to see. So the flux is directly proportional to square root of the temperature, and if you want, we can compute n from pressure and temperature to have another expression. But yeah, this is one of the other points. We have computed the molecular flux. The next one is going to be the pressure. If we want to compute the pressure due to the gas, right? So this is going to be point G. Remember, pressure of gas, pressure in general, P, little p, is like defined as force divided by area. Right. So one can think of molecules hitting a wall and bouncing back. So if you remember this cartoonic sketch, these dots are like gas molecules, and they move randomly, random directions. So if we take a particular side of the container, we can imagine that the molecules would hit the walls and then bounce back, right? And that is actually what sources pressure. So for such molecules, for a molecule that hits a wall and bounce back, So if we assume that there isn't loss of energy and so on and so forth, one can compute the absolute change in momentum of the molecule. Okay, if we call that, let's say, delta momentum, this is going to be equal to momentum after hitting the wall. So we want the absolute, so momentum after hitting the wall minus momentum before hitting the wall. Momentum after hitting the wall, if we assume that the molecule bounced back, so the velocity is reversed, this is going to be, let's say, minus mv cos theta. Just remember that we are considering molecules like traveling with velocity v and then hitting a wall, but we want the component of this velocity which is perpendicular to the area under consideration. Right. So for that reason we're going to use v cos theta for computing the momentum. So momentum after hitting the wall is minus mv cos theta minus momentum before hitting the wall is mv cos theta, and we want the absolute value. This is going to be equal to 2 mv cos theta. Now, using definition of force to be equal to mass times acceleration, Vm dv by dt, and we can write this as dA change in momentum by dt for m constant. Okay, so this implies that force times dt is going to be delta change in momentum, called the impulse. Okay. Therefore, with this, we can compute pressure due to a molecule. Let's say is going to be F divided by A, and this is F dt divided by A dt. We can write it in this way such that we can use the impulse which we have computed earlier in the previous page, that is changing momentum, is F times dt, which we have seen it is going to be equal to 2mv cos theta divided by A dt. So this is due to pressure, kind of due to one molecule, and for many molecules the pressure due to molecules is going to be equal to P molecule times what we have computed earlier, point E, times number of molecules hitting a wall of area A, times number of molecules hitting a wall of area A, right? And so we just substitute these 2 mv cos theta divided by A d theta dt times number of molecules, which we have computed earlier. It's going to be A v cos theta d theta dt times n f of v dv times 1 over 2 sin theta d theta. Okay, so A and dt is cancel. So we're going to have an expression for pressure due to molecules, and then we can compute total pressure by integrating this pressure element, okay, because this pressure of molecules is the pressure which comes out due to or from molecules which are having from molecules with speed between v and v plus dv, and molecules traveling in a direction to our reference within theta and theta plus d theta and hitting the wall. Okay, so we would want to integrate over dv and d theta to compute the total pressure. Thus, pressure of gas P is equal to we integrate dv from 0 to infinity, integrate d theta from 0 to pi divided by 2 p molecules, right? So this is 0 to infinity, 0 to pi by 2 2 mv cos theta v cos theta n f of v 1 over 2 sin theta dv d theta, right? So you can rearrange this to be m times n integration from 0 to infinity of dv v squared f of v and 0 to pi by 2 d theta cos squared theta sin theta, right? Again, one can see that this is sort of average speed squared, what we have done earlier, and one can check to see that this integration is going to be equal to 1 over 3. Okay, so making these substitutions is going to imply that pressure is going to be equal to 1 over 3 mn average v squared. Okay, so you see, this is really fantastic. Using kinetic theory, we have using statistics, method of computing average, one can like predict the pressure of a gas. You just need to know the number density. Number density is n is equal to small n over v. Average of v squared, we have computed the integration earlier. It's 3 kBt divided by m. Right, so with these substitutions we can see that pressure times V is equal to n kBt. So this is another form of the formula for pressure, or one can write it as kind of a P is equal to n kBt. Or PV is equal to nm RT. Okay. Where R is gas constant. Sorry. R is equal to gas constant. Yes, Avogadro's number Na times Kb. Yeah. N little nm is number of moles in the gas under consideration. Number of moles, which you can compute as total number of gas molecules, big N divided by Avogadro's number, Na. Okay, so hopefully with this you can see this nice formula for pressure, and from here there are some notes which we can derive. Note that. So P is independent of mass, okay, given that P is equal to n kBt, implies that pressure is independent of mass of the gas molecule. Okay. Can compute average kinetic energy. Average kinetic energy of the gas U is equal to number density times 0 to infinity 1/2 mv squared as the kinetic energy of molecules, f of v dv. Okay. So this is equal to 1/2 nm v squared. And from this we can see that pressure can be written in terms of the average kinetic energy in this way. It's going to be 2 divided by 3 times average kinetic energy. Right. Well, for relativistic gas, this is going to be different, and this is a topic which is going to be addressed hopefully sometime later. Finally, one can consider a container having like different types of gases, right, of gas molecules, right? So for a mixture of different gas molecules at thermal equilibrium, the total number density is going to be equal to summation over I for the individual number densities. So I is going to be 1, 2, just a label for the different types of gas. So the number density of gas molecules 1, right, is just some n1 plus n2 plus n3, and it goes that way up to the number of different types of gas molecules. It could be 2, it could be 3, whatever, right? So from this individual number densities, you can compute this total number density and use that. One can use that to compute the pressure of the mixture of gas. So this is going to be n kBT, and it's going to be summation over I Ni kBT, and this we can call to be Pi, so this is going to be summation over I Pi. Okay. This is also known as Dalton's law. Dalton's law. Okay, that's it for the pressure. We have an expression for pressure of gas. The next thing we would like to address is about molecular effusion. Okay. Escape of gas via a small hole or something. Okay. I think that's it for now. Until next time, I say goodbye. Take care.